the environment around you, you can instinctively algorithm that we are using for perseverance. And humans drivers is that human has instinct, right? Right the moment when you see the environment around you, you can instinctively think, hey, that's the rock that you have to avoid. There's an open space over there. You don't have to think much, right? So I thought, can we replicate that kind of instinct by using machine learning? Yes, we can. We can train the neural net to tell which part of the terrains, which path options are more promising than the others, so that it can accelerate the planning algorithm. This is just two of many examples, but there are a lot of possibilities, by applying the latest technologies to, help future spacecraft more, safer and more efficient.
Well, in talking about this and planning this talk, I was thinking about this as I drove home about how I naturally know when to hit the brake. I know how far away
Yeah.
I'm going to be. How you said the word train. How do you teach something like this to a machine?
Yeah, that's a good question, right? Uh, any of my attempts to teach something to my daughter miserably failed. So I know how hard it is to teach, right? Something to, you know, um, well, at least artificial neural net is not as rebellious as my daughter. So maybe that, anyways, so, um, yeah, but training the artificial neural net, particularly deep neural net, is challenging because it requires huge amount of data, much more than your kids require. So in the case of terrain classification, for example, right, you typically need tens of thousands, maybe hundreds of thousands of examples to make it reliable. So where we can get that data, right? So that was one of the challenges that we faced. We tried a few different things, but in the end, what worked very well was to get help from people on the internet.
Okay.
Can you go to slide 14, please? So during COVID, we launched this project called AI for Mars on internet. It's on the site called Zooniverse. Basically, it's like, we said, hey, everyone on the internet, would you kindly help us to create the examples to teach them over? And actually, many people say, oh, yeah, right? So it's very easy. Anyone can go to the site. You can Google AI for Mars, number 4, stylized, and, open this page, and you can view the real images for Mars. And all you are asked to do is to put these bounding boxes around rocks, around sand. This training data comes to us, which is used to train our neural net, which might be used in future spacecraft. So I'm glad so many people were excited. We got, I think, 50,000 volunteers in total. We got, I think, around 600,000 labels, inputs from people. So I really appreciate people's passion to help future spacecrafts make it smarter.
I, I like that you use the phrase passion there because we'll do anything for Mars and for these things. But JPL is more than Mars, right? We talked about Voyager. We're talking about all these other
Exactly.
places.
Yeah.
Let's go beyond. How does autonomy help us beyond the red planet?
Yeah, of course, Mars is not our final destination. It's one of the closest planets, and beyond the orbit of Mars, there are more interesting things, unexplored, waiting to be explored, right? Can you go to slide 17? One of those fascinating and underexplored worlds are these icy moons of gas giants. Around Jupiter, Saturn, Uranus, and Neptune, there are many moons, mostly made of ice or covered by ice. Europa, Ganymede, Callisto, Titan, Triton, and Enceladus. Those are just a few examples. They're fascinating because many of them would likely, not all of them probably, but some of them have subsurface ocean. There are liquid water ocean, right, below this thick shell of ice. Likely Europa, likely on Enceladus, maybe on Titan, maybe on other moons. And some of them, are considered potentially habitable. No one knows if life can live there, if it's there or not. But some scientists suspect that these oceans could be habitable. Among these icy worlds, one of the most fascinating worlds is Enceladus. Can you go to the next slide, please? Slide 18. Enceladus, this is a relatively small moon of Saturn. It's about 500 kilometers across. The surface area is around about Texas. So what makes this world unique is this geysers, found by Cassini when it flew near the south pole of this moon. It found that something was splashing out of this moon to space. It turned out that this is a water vapor, likely coming out from rings of Saturn. So, it's fascinating in many ways, right? But one reason is that, hey, this could be, a great pathway for us through which we can exploit. Let's explore more with the next slide 19. This is, what scientists imagine the interior of the moon is. Again, as I said, there's a shell of ice below which there is likely a liquid ocean, and around the South Pole there is conduit, geysers. So we thought, can we make a tiny robot that can dive into these conduit, goes down all the way to the ocean, and possibly, meet life if there's any. So can you go to the next slide, please? 2016, my colleague and my friend, NASA's Innovative Advanced Concept Program, to take a closer look about this seemingly. So can you go to the next slide, please? Some years ago, in 2016, my colleague and my friends and I got this, relatively small funding from a program called NIAC, NASA's Innovative Advanced Concept Program, to take a closer look about this seemingly crazy idea of sending robot down to this, active vents, and studied if it is ever possible or not. Skipping all the way to the conclusion, we found that, of course, no one knows how it looks like below the surface of Enceladus. There could be, infinite number of possibilities, but, there are two, super roughly speaking, the reality could be more complex than this one. But super roughly speaking, there are two possibilities. One is that, that this vent is, wide open. There's a clean interface of the water from which the water boils and somehow accelerated and goes to space. The other possibility is called cryovolcanic model. It's basically inverted rocket nozzle. The high pressure liquid gas mixture goes up the vent and gas expands that propels the jet. We found that this idea of letting the robot going down the vent is likely possible, likely feasible for open conduit model. It would be possible for cryovolcanic model. It is harder, but if the vent size is more than 10 centimeters, which cannot be guaranteed, but given that there seems to be more than hundreds of vent openings, what's a chance that we can find at least one vent that is more than 10 centimeters? Probably is quite likely. So, can you go to the next slides, please? We, did some experiments in the working freezer, and also, next slide, we run some CFD. computational fluid dynamics, and then we arrived this robot. Can you go to slide 22, please? Yeah, one more. We, felt, okay, so this could be one way to make this happen. A tiny robot, maybe, again, 10 centimeter in width, maybe 30 centimeter in length, has a few limbs. At the end, there are ice screws, possible designs, and, we are actively exploring, more promising designs. But yeah, so, this could be a fascinating, idea. And then, of course, this robot is going to, go into this vent, which has so many unknowns, right? You cannot fly your spacecraft above it and, make a detailed map. So, it has to deal with uncertainty. It has to move vertically. You have to control this complex robot to do so. And also the environment is dynamic. So there are so many reasons that this robot has to be, again, highly intelligent.
So, Hiro, I want to jump forward and loop back. I want to talk about Voyager again and talk about autonomy in something like this. And if we go to our next image, you can truly see how alone it is out there. Talk to me about something like this and what is truly, after you being here for 34 years after this and all these great things, talk to me about that.
Yeah, it's amazing, right? It's fascinating that this spacecraft, keeps flying after 34 years, when I was inspired, right? It's still flying beyond the heliopause, into the interstellar space. And interestingly, there's no other spacecraft still that, went beyond, where Voyager is, right? But surely someday, we should catch up and move beyond, right? We gonna explore the icy moons of gas giants someday. We're gonna go to the subsurface ocean. We're gonna probably go back to Neptune's system someday. In particular, its moon Triton, which is very interesting. Maybe KBOs. We know there are many Pluto-sized dwarf planets beyond the orbit of Neptune. Eventually, maybe interstellar space, right? Like TRAPPIST-1 system, which has multiple habitable planets, which may take, hundreds of thousands of years to get there, maybe, yeah. So, thinking about Voyager, right? It already happened. Sometimes, after a success was made, we often kind of take it granted, right? It's hard to imagine how innovative it was. But if you put yourself from the viewpoint of the past, this idea of grand tour, right? Visiting 4 major planets, gas giant planets, in one mission, which basically what Voyager 2 did, was initially conceived in 1965 by this graduate student named Gary Flandreau. And that time, 1965, what JPL did and what whole world did actually was to send only 2 spacecrafts successfully to other planets, right? One to Venus, one to Mars. And, that time, this guy was talking about building a spacecraft that lasts tens of years and going all the way to Uranus and Neptune and eventually to interstellar space. What you're talking about, right? That was the craziest idea at the time. No one believed it, laughed at it. But, but it happened eventually. JPL made it happen. So Voyager reminds us that, JPL is a place where grown-ups are allowed to dream big, right? And it's a place where those big dreams are turned into reality.
With that reality, before we started this talk, you were holding your child in your arms.
So Voyager reminds us that, JPL is a place where grown-ups are allowed to dream big, right? And it's a place where those big dreams are turned into reality.
With that reality, before we started this talk, you were holding your child in your arms while you were setting up.
Yeah.
How, when you look at this and look for what's next, not just for this mission, but for all these missions, but for also life, I mean, how is this working for you?
Yeah, I mean, life means my personal life, right? I guess.
Yeah, I mean, I can hear it around you too. I can hear it right now live. It's a very exciting life you got. Yeah.
Yeah. So why don't you show the last slide? Yeah, that was actually last weekend. The Jupiter and Venus were at conjunction. So I took my daughter to the front yard and pull out this the telescope from the garage and looked at the planets. I'm still getting stars. After 35 years, when my father gave me this telescope. Not with my father anymore. With my kids. I like this. I like this a lot. To getting stars still. I think for two reasons, right? One is that I said JP is a place where we can dream big, but of course, we are not, thinking about big things 40 hours per week every day, right? There's so many, little things to bother, right? Just like any other workplace, that's the way that humans make progress.
That is the way that we make progress. Thank you so much, Hiro. There have been a lot of great questions out there on all the platforms, so I'm going to throw it back over to Rachel. How's it going out there, Rachel?
Oh, goodness. Okay, I'll tell you. We're not going to get to every single question. I think we maybe have time for about five or so. 4 to 5. Well, let's see how many we can get through. So, Hiro, there's so many amazing questions.
Rachel, can I interrupt you for a second? Your audio is getting a little out there on all the platforms, so I'm going to throw it back over to Rachel. How's it going out there, Rachel?
Oh, goodness. Okay, I'll tell you. We're not going to get to every single question. I think we maybe have time for about 5 or so. 4 to 5. Well, let's see how many we can get through. So, Hiro, there's so many amazing questions.
Rachel, can I interrupt you for a second? Your audio is getting a little fuzzy right now, so I'll ask the first one that you've highlighted for me if you want to reload, and we can ask that back in. So Akshay on LinkedIn wants to know, did you find any differences or surprises in training Perseverance's AutoNav on Earth and when it started operating on Mars?
Great question. Yeah, maybe the biggest surprise is that it works so well. Right before we activated the AutoNav, my worry was that, what if my codes, maybe that's a positive surprise that I had.
Very cool. Rachel, are you back with us?
I hope so. Am I back?
Yay!
Yes.
You sound great.
Welcome back.
Okay, thank you. Sorry, everyone out there, for the audio issue, but I'm glad to be back. Okay, so Mace Bob on YouTube asks, to you, Hiro, do you think we're close to a robot being able to decide to pursue discoveries that the mission planners were unable to identify?
Unfortunately, we are far from it. In my opinion, yes, artificial intelligence made really impressive progress in the past, I guess a decade or so. Everyone knows about it. There are so much news about ChatGPT, for example. But, in general, AI works very well as long as its inputs and outputs are confined within computer network. But, when, it has to handle the real world, it has to handle physical interaction. It's still way behind. For example, I'm a Japanese, so I can easily pick up tofu with chopsticks, right? That's a very hard task for robots. Picking up rocks, drilling a hole, So, I don't believe that AI or or autonomy gonna take over humans, particularly into its physical interaction and creativity. So, it's still far from the time when AI will replace our scientists, in my opinion. But AI is our helpful friends, and as it gets more and more capable, if it can do just 1/10 of what humans can do, we can just move way beyond.
Yeah. Oh, wonderful answer, Hiro. So we have time for 2 more questions. But on a similar note, and I really like
an engineer's design, right? Instead of let it learn by itself, right? So engineers design how it could behave, and you turned on, then it keeps going, right? There are learning algorithms, and there are algorithms that needs to be supervised, that needs examples to be trained. There are algorithms that can self-train, it can teach itself. There are algorithms, it gets feedback from people, like teacher and students. Students, do some work, and teachers gives feedback, and so there are many different ways. So we cannot say, I cannot give a simple answer, but it depends.
Understood. Okay, last question. I'm sorry to not get to all of your questions. They are actually amazing, so I'm hoping we can send all of these over to Hiro, just so he knows what's on your mind.
I spoke too much. I should have.
No, you didn't. You spoke just the right amount. This one I'm very excited to ask. So what is one of your favorite moments that you've experienced of our solar system through a robot?
Oh,
it's a good one.
The question was, what's the best moment?
Yeah. Essentially, what's your favorite moment, right? Operating these rovers, you've experienced something that so few people get to experience. Maybe you can think of one moment. I'm sure there's many, though.
Yeah, I think it's still the landing of Perseverance, the moment, because, it's not because I was involved in landing. That was not my job. With thousands of people, spent so many years to, make this happen. And it hinged on this, 7 minutes of terror. How this, autonomous robot can do is showed by itself. And we were so anxious to watching it. And when this, confirmation signal came back from Mars, we are on Mars, that was really a, moment for me.
Amazing. On that note, Brian, I know you will close us out. Thank you.
Thank you. No, Mark, Curtis, Nikki, Amanda, the Kims, Joey, and everyone behind the scenes who make these public talks possible. It truly does take a team. I would like to thank our co-host Rachel and our speaker Hiro for the passion, expertise, and general awesomeness. Our final thank you is to you, the audience, who join us every single month. This is your space program, and it is our honor to bring you these monthly talks. Stay safe, stay kind, stay curious, and we'll see you next month.
There's one thing that stands between us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island. On the island of Svalbard. The island lies beneath one of two regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is how did Earth's atmosphere evolve over time? And how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative, CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp.
And we don't want to waste our rocket. It'll take us 3 years to make the rocket and only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this?
These iridescent colors. 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the ISCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the North and South poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight.
Can you guys hear Hjalmar? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish.
T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.